Okay, so welcome back to another video. In today's video we have a little calculus problem here, and we are given that if f be a differentiable function such that with the following condition that we have the composition f of x is equal to x for all x that's in the closed interval 0 to 1, and also given that the defined value for f of 0 is equal to 1, we want to calculate the following definite integral. This integral from 0 to 1 of x minus f of x quantity to the power 2016 dx. And it's not as, complicated than you'd think. It's basically just use the idea of how we can use the whole idea with the composition of the function over here and do a little bit of analysis here, but also of course this is calculus as well, so basically it's just using the u-substitution once we come to the idea of what we can use for that composition over here and the defined value. Other than that, I don't really have any other comments, so we can actually just jump in. So let's start off by seeing that given with f of x is equal to 0, and we're also given that f of 0 is equal to 1. So let me first just define our composition over here. And then we're also given that f of 0 is equal to 1. So then if I were to plug the our defined function into the composition, so we get that f of 0, and of course that's actually saying that's also, in other words, it's f of 1. Then we can see that we plug 0 for x, then we're going to get that f of 1 is actually just equal to 0. So yeah, so we got that. So let's actually suppose that we actually define some function in terms of a function f. We let f of x, we're going to call this such that it's let f of x equals t, right? And then what I can do is if we were to plug the composition back in, so that means f of x, that would be equal to f of t, such that it's also defined as equal to x. So what I can do is I can actually do the substitution, well, u-substitution, but then first we got to differentiate. So we can say that f prime of t dt is equal to dx. Okay, so we have that. So now we can actually jump into calculating this definite integral. So I can calculate this. We'll call this capital I, and that's defined. We have that 0, 1. I'm just gonna basically just write out this again. F of x to the 2016 dx. We see that if we actually perform the substitution, don't forget we had to calculate our bounds. So let's see, we have x is equal to 1, right? So we say that x is equal to 1, then we say that f1 over here, so then that's going to be equal 0 for the top bound. And then if we set for 0, we have that f of 0 is equal to 1, so that's going to be 1 over here. We do some substitution. We say that x is equal f of t, and then we say minus f of x, where we define that f of x is equal to t. So over here, this will be a minus t, 2016, and then we replace the dx with our f prime of t dt, so like so. And then what's nice is we can actually, so as you see that we have to switch our bounds because we have that 1's the bigger number than 0 with the whole as the lower bound. That's not possible, so you have to switch this. That will become negative, so then that way that becomes 0, 1. And what's really neat from inside the quantity over here is that I can actually just rearrange the terms so that we start off with t. We'll preserve the subtraction symbol, minus f of t to the 2016 power, then f prime of t dt, simply because we have an even degree of the exponents, so it's always going to remain positive. So it doesn't matter how you interchange your terms, it's always going to be positive, so it still remains the same. So we have that. So now what I can do is I'm actually going to double the quantity of I, so we have 2I, because they match the same thing, they're equal to each other. And I'm actually going to take this term and then add it with this term. So this will be this integral minus this integral. So let's see, 0, 1, x minus f of x 2016 dx, and then we can subtract this with this integral over here, t minus f of t 2016 f prime of t dt, but that's also equal to, since this is just this is just a dummy variable, so I can just replace this back with x. They actually match the same thing because we showed that they're equivalent to each other, as you see over here with these steps. So this is the same thing, 0, 1, x minus f of x, 2016 dx. Or rather, what I can do is we can actually combine the two together using the fact with linearity. Well, how about this? You can see that if I just replace the x back here, then we can actually see that this actually forms a binomial expression, so I can actually unfoil this. So I can factor out, in this case, for example, if this is x minus f of x to the 2016 power, they both share the same term, so I can actually distribute that out. So this will just be multiplied with 1, and then minus distribute with over here, so this will be f prime of x right over here. Then dx. Now calculating this integral is very simple. We can actually just do the u-substitution over here. We let u equals x minus f of x, then du is equal to 1 minus f prime of x dx, and you'll see that that actually just cancels that out. So we're just left with, so let's see, this will just be, in this case, u to the 2016 power du. Then that's easy to see that this is just, so substitute this back in for x minus f of x to the 2017 power, and then this is divided by 2017, right? And then we just evaluate our bound from 1 to 0, and then you'll see that if you actually just evaluate your bounds. Let's see, if you plug 0, so this is 0 minus f of 0, which we said that's 1, so that'll be a negative. And then if we plug 1, so it's 1 minus f of 1, where we said f of 1 right over here, that's equal to 0. So that means this is 1 minus 0, and then, so this will be 1 over, I'll write like this, this will be 1 over 2017 minus negative 1 2017, which is equal to positive 2 divided by 2017. However, you see that we said that that's 2i is equal to this value, so all we gotta do is just divide by 2. So I'm just gonna jump over here. So we say that 2i is equal to 2 divided by 2017, divide both sides by 2, and we get that the final answer is just 1 divided by 2017, like so. And there we have it. We said we've shown our, we evaluated the following definite integral with the conditions over here. So yeah. That's pretty cool if you ask me.